First, I would like to thank the organizers for hosting this excellent event and also kindly inviting me to speak here. My talk here is about geometric hydrodynamic. Geometric in the sense that in the way that Arnold introduced it in '66. My talk is slightly deviated from the abstract that I sent for the event, because I found some interesting results in between that I would like to present them here. So first, basically, I will talk about three nonlinear partial differential equations. The first one is the vorticity form of the Euler equation for incompressible perfect fluids on the sphere, which is given by I call it Euler equations. So for this talk, the manifold is just a sphere. I consider the fluid on the sphere, on the surface of the sphere, the two-dimensional sphere. And the next one is quasi-geostrophic equations, which here the potential vorticity is different plus or minus some beta. I have to say that what is z and beta and alpha, this is called quasi-geostrophic equations. So alpha and beta, they are constants. Beta comes from the approximation of Coriolis forms with linearly with respect to its distance from the equator, and alpha is called Froude number, I guess. So I use this coordinates for a sphere. So we have two angles, but we call this one z. And we have another angle which is called lambda. This is basically co-latitude. So this equation firstly was geometrically studied by Reitlin and Passmanter, and then on torus by Cornelia, and after that by Ebin and Preston in 2013. The next equation is global quasi-geostrophic equation, which the potential vorticity is different. This one is not constant anymore. That's the big difference. Plus some terms which comes from the Coriolis effect also. This one also comes from Coriolis effect. It's 2 by some number called Rossby number plus some function. This is a function generally. Again, gamma and Rossby numbers, they are constants, but h could be a function which encodes the topography that they considered in this simplified model. This is called global quasi-geostrophic equation. This equation was firstly introduced by Schubert and Berkeley in two different papers by two different approaches in 2009, and last year Lewising and co-authors, they introduced it in a mathematical way, but not as an Euler-Lagrange equation. What we will do today is to study a little bit the geometry of this, the configuration space of these equations of these nonlinear PDEs, and see that what we can talk about the line time behavior of their solutions using geometric tools, basically curvature and conjugate points. let us start with some pre-quantum bundle that Cornelia introduced last week. But on this pre-quantum bundle, we consider two different metrics, weak metrics, that I will introduce. And they present different dynamics. The pre-quantum bundle is the Hopf vibration from S3 to S2, which is a non-trivial second bundle. And elements of this S3 can be represented by two complex numbers, for example, W1 and W2, which they have norm 1. And in this setting, the projection is given by just this map pi, a real number and a complex number.
Sphere, you have to change constants.
Yes. So a sphere is here is with radius 1/2. So on the other hand, so we can identify S3 with a Lie group, special unitary, via this map F, which basically helps us to define three left invariant metrics, right invariant metrics, vector fields in the Lie algebra, using the Lie algebra elements E1, E2, and E3. So using this vector fields, we induce a metric on S3 also. So we assume that these vector fields are orthogonal in norm 1. We consider, in the next step, we consider a dual for these three vector fields. The first vector field, so it's important. So we denote it by E. This is the rib field, which is a killing field for our metric, and it would be important for finding the quantumorphism group. Hence that we use a dual for this, a dual basis of one forms, and we call the first one, which is dual to rib field, by theta. A quantumorphism group, which denote the letter Q for that, an S3 of Sobolev class S, all those diffeomorphisms which they preserve this one form theta. So they preserve the rib field as a result. HS here means that the diffeomorphism and all of its derivatives up to order S, they are all in L2, in the L2 space. Levin and Preston in 2013, they proved that this group admits, for S big enough, admits a C infinity manifold structure, and also it's a submanifold of those volume preserving diffeomorphisms, which also they commute with the flow of the rib field. Basically, this is they are contained in some volume preserving diffeomorphisms, which they have also symmetry. So one of the important things when we studied equations with Euler, with Arnold approaches to understand the Lie algebra. The Lie algebra of this group. Of course, this is a group. Right translation is smooth, but left translation is not. And inversion, they are not the smooth. Because of that, it's a half Lie group. And whenever I say Lie algebra, so I mean tangent space at identity. When you let S to be infinity, in the sense that you take intersection of all these Sobolev manifolds, then it's a Lie group. Then that's it. But if directly you go to this threshold category, then you lose some tools like existence of solutions for differential equations.
question. In your definition of quantumorphism group, I think theta is a one form on SU2. So are you implicitly factoring the map from S3 to SU2?
Just from S3 to S3,
I mean,
which they preserve the one form.
yes, and theta, like in this relation,
Yep.
theta is a one form on SU2
Yep. But
on S3. So my question was if you are implicitly factoring this map F
yeah,
in that
we use this method.
equivalent.
In fact, we use this as an isometry.
Yeah.
We pull this vector fields into S3 with this map F.
Yeah. I just wanted to know if you just didn't write this map F in this equality. But yeah, thank you for clarification.
There are computations which I did it with different notations, which they could be confusing with different angles, but this was the dense way to present it. Yes, please.
So this theta is your contact force.
Yes.
On S3. So that's why the vector field appeared. I mean, the
Yeah.
name appeared. And so those maps are strict contractomorphism. Yes.
Yes.
That preserve the form, not only the distribution.
Yes, that's correct. That's if we want to just for in the case that you mentioned, we have to consider contractomorphism, which is different, also studied by Emin and Preston.
These matrices are up to some constants, the Pauli matrices.
Yeah. So we consider the space of all HS plus 1 functions f, which they are E invariant, and they will play the role of the stream functions for Lie algebra elements. Let's denote the tangent space at the identity of this Lie group, which curly G, and then so the elements of this Lie algebra, this tangent space, can be obtained using a stream function and some operator which called S theta. It depends on theta and E. And so on a sphere, on a street, it is explicitly given by this one. It differentiates in the directions of E2 and E3, and so this is E invariant and doesn't make sense. So in the next step, we define some weight function which will be used to define two metrics on S3, on quantumorphism group, and also. So rho is a function from S2 to R, and we lift it to S3 using the projection, and we call it the same rho. This will play the role of a weight function in the sense that, so consider an operator A from vector fields on S3 to vector fields on S3, which sends every vector field. The second and third components remain the same, but first component is multiplied by some rho square. Because of that, I called it weight function. And we use this operator A to define a metric in that Lie algebra. So as it's given here, basically we consider this rho square here. That's if rho is, and this bracket means just integrate on S3 with respect to the volume form on S3, which was given by those orthogonal fields. So if rho is a positive constant alpha squared, rho square is a positive constant alpha squared, then we denote this metric by power alpha. We have two different metrics, power A and power alpha. So this one, basically, when you are away, you move away from the equator, then you see the difference of the norm of the tangent vectors. On the equator, something vanishes. This term vanishes. So if rho is a function which shows the distance from the equator, basically the rho that we will use is this function. Write it down here. basically distance from the equator. It will describe that some effect vanishes in this equation. Yes, please.
Are these operators somehow related to the action of the unitary group on S3? S3 is the unit sphere in C2, and the unitary group acts canonically on it. And so this is a part of the structure. And the diagonal unitary group, the quotient by the diagonal unitary action is the complex projective space. Yeah, so this is the space of pure states in this two-dimensional case. So, yeah, so because you write down certain formulae, so maybe that some of them are related to this unitary action.
I don't know exactly, but so this is an inverse approach to this equation. So we have this equation and we want to show the existence of solutions. This for short time and then for long time, and also dependence on the initial conditions. Then study it. So that's the reason that I define that method, that operator A. But if there is other descriptions, already I'm not aware of that. Well, so we have quantumorphism group on S3 and also volume preserving diffeomorphisms on S2. So using the projection of half vibration, we can define a projection from this quantumorphism group to volume preserving diffeomorphisms, because these diffeomorphisms are all invariant and it's well defined when we define it. So you take an element of the orbit and then project it out. So, and the point is that if you consider this quantumorphism group with the metric power A, and you consider the volume preserving diffeomorphisms with this metric, this part is important. That one, we will kill it somehow. Then we have a Riemannian submersion. This was done by Ebin and Preston for the case that rho is equal alpha, and the proof is very much like that for the case of rho. So we have different concepts, we have different multiplicator, different weight function, and so constants. What does it say? That's the important thing. It's the same part of the metric, but with a different explanation. We consider the L2 metric of the velocities, and also we consider the stream functions themselves. That's the role of the first central extension that we described by this pre-quantum bundle. That's the role of this first central extension. The cocycle is trivially 0, but it appears in the metric. That's the role that it plays here, with this rho square. So this map pi with this matrix is a Riemannian submersion, and the Euler-Arnold equations on the base, volume preserving diffeomorphisms on S2, is given by equation 3. So we see that somehow like that, without this part, without this Coriolis part, which comes from the second central extension with a non-zero cocycle, but again trivial. This is an Euler-Arnold equation. So basically, you have to compute this co-adjoint operator with respect to this metric, and then you get it. You have to make a specific choice of this representative Hamiltonian function of this vector field. Somehow it's unique. So the next step is that, so these Euler-Arnold equations, they are somehow integral curves of some vector fields on the manifold. let's see what we can talk about their solutions, the existence of the solutions of this nonlinear PDE here. This one by. So in the absence of this one, this term, the solution exists for short time and the dependence on the initial condition is smooth. That comes from this usual Picard-Lindelof theorem for smooth vector fields on Banach manifolds, on Hilbert manifolds here. And if we choose the initial condition to be smooth enough, then the geodesics exist for all the time. This was proved for that metric alpha by Evin and Preston, and then by Modin and me just a couple of months ago. For this new metric, the proof is very much the same. The proof is simpler. Why? Because in this work, they consider the general case and the computations are longer, but here, since we consider just a specific vibration, the proofs are shorter and more. But we had to do that, I mean, to see that it's really an Euler-Arnold equation and we can talk about its geometry. Now we have a configuration space, we have a configuration manifold, we have a weak Riemannian metric, weak in the sense that it generates the topology which is weaker than the HS topology. It's just kind of L2. And we can talk about exponential map, Riemannian exponential map, which sends data to solution, initial condition to solution at time 1. So basically, I will focus on this group of volume preserving diffeomorphisms with the metric that we introduced, but it's the same story for quantumorphism group. The exponential map is defined by sending U0, the initial condition, or the Lie algebra element here, to the solution at time 1. Kind of, so we have two different pictures, Eulerian and Lagrangian. So we have a group G, which G is here, the volume preserving diffeomorphism. We have a Lie algebra, which I denoted it by G tilde. So once you have a curve here, so it could be the whole real line, then you can find a curve in this group, a geodesic in this group, in fact, by eta. And eta and u are related by the right logarithmic derivative. If you have another description of this Lie algebra, according to stream functions, then you have another candidate, stream function. So here you look at the velocity fields, but here in this Lagrangian picture, we move with the particles and we see that how they move. What is the velocity field of the particle x at time t? You have a solution of the Euler-Arnold equation, you have a solution of this equation partially, and you have another geodesic also. So we consider the geodesic at time 1. This kind of data solution map. The singularities of this map, of this exponential map, are called conjugate points. In the sense that we differentiate it at this point, for example, then the tangent space is just a vector space. Tangent space is itself, but here we have another vector space. Then we have a linear map between Hilbert spaces, and we can talk about its kernel and co-kernel. Elements of the kernel are called monoconjugate, and elements of the co-kernel are called epiconjugate points. But in the case of the 2D perfect fluid, This is a nonlinear Fredholm map. But I didn't show the proof for this central extension case. So I suspect that it's the same. Fredholm map. But how to find these conjugate points? We will find these conjugate points using Jacobi fields. Suppose that we have some initial velocity u0 and we issue some geodesic eta in the group of diffeomorphisms. Let's perturb this initial condition a little bit. Perturb it and just issue another geodesic. So if we change S, then we have a two-parameter geodesics, eta, S, and T, and we differentiate with respect to S times 0, and we call it J of T. J of T is this one. This fields along the geodesic eta. So J of T just is defined by this expression. So obviously J of 0 is 0. What happens if there is an instant T0, which J of T0 is also 0? Then it's like that. Perturbed geodesics comes to the original geodesic at time T0. And this is some kind of effect of the positive curvature of the configuration space. Arnold, in his paper in '66, he computed the sectional curvature on the group of volume preserving diffeomorphism on torus, 2D torus, and he noticed that most of the directions is non-positive. As that can be find conjugate points. The first one who did it was Gerhard Mischuwer in 1993, I guess. And in another work in '96, he introduced a criterion, we call it M criterion, which if this criterion for some initial conditions U0, U and V is positive, then there exists a Jacobi field which, and time T0 positive, which we have conjugate. We will use this one to see. And also if this criterion is positive, we know that the sectional curvature is also positive. So let's go to the case of the sphere, specific case of a sphere for these equations. We will use a set of exact solutions of these equations, which are generated by spherical harmonics. These are Legendre associated polynomials, and this is just usual complex exponential. L and M are integers with this condition. If M is 0, then we call them zonal spherical harmonics. They only depend on the condition, on the distance from the equator, not the angle. Kind of so form an important set of exact solutions of these equations. Structure constants. So for any two spherical harmonics, one can compute the Poisson bracket according to structure constants. They are complex structure constants. They are complex numbers, which is the same for the corresponding Hamiltonian vector fields. And the real structure constants, they come by this term. And they could be computed according to Wigner 3J symbols. This kind of nice form of these structure constants, but these Wigner symbols are kind of complicated to manage. Cyclid model plus was trying to avoid computing these Wigner symbols by another method. In this result, in some part of these results, it's not that horrible to compute these things and also even prove something for general wave numbers. If we relax the situation a little bit, in the sense that, so we can write this M criterion for quantumorphism group with metric A and also for the corresponding Riemannian submersion, that metric on the downstairs on volume preserving diffeomorphisms. This one is important basically when we come down, and so we look at this equation for this one. If rho is a constant, then we have this equation. Basically, when rho is a constant, then this term disappears. This term is kind of important. This parameter is called Lamb parameter, and it differs for different planets, for different circles. It depends on radius and horizontal scale, several things. But mathematically, we see that this term appears here. If this is a constant, then this term vanishes. What is this M criterion index? Nu is just the usual criterion that Gerard used for the group of volume preserving diffeomorphisms on S2. And it could be computed explicitly for this spherical harmonics, using this expression. It's kind of not so bad. It's better than, a little bit better than differentiating many times and computing that. So in fact, James Ben, 4 years ago, published a paper for conjugate points on volume preserving diffeomorphisms in this setting. And he didn't use this structure constant. And you can have a look at the paper. So huge computation for if we avoid it. Let's see the difference, a little bit the dynamics, a little bit the behavior of solutions and the difference of these equations. So for now, we do not consider these terms. Terms will appear in this next central extension. Let's look at them. So, trade wind was first used by Vladimir Arnold to say something about unreliability of long-term weather forecasts. In this setting, we know that in the most of the directions, when you perturb this velocity field, a little bit, then you have mostly negative curvature, not non-positive curvature. Basically, this trade wind is an effect of the difference of the temperature on equator, is a simplified model, and the poles, and the effect of the rotation of the Coriolis effect, which is deviated a little bit to right in the north hemisphere and to left in the south hemisphere. So, can we find directions with conjugate points in this setting if we assume that this stream function is given by z squared or trade wind? The answer is no. This criterion cannot detect any conjugate point. It's always negative. This was proved by Tauchi and Yoneda. What about this quasi-geostrophic setting in the absence of the Coriolis force? It's again no. But here, yes, the answer is if you choose a proper gamma, then yes, you can find conjugate points. And not only in some directions, in the most of the directions, in any direction, for choosing any G, which G is non-zonal, you can find positive curvature. This is kind of a stability effect. If you perturb it, it comes back a little bit. That's the difference. That's one of the differences of these equations, of these nonlinear equations. What about just non-zonal spherical harmonics? Well, Preston and Labrigant, last year they published a paper and they considered group of volume preserving diffeomorphisms on two-dimensional torus, and they considered the counterparts of the spherical harmonics on torus, Kolmogorov flows. and they prove that for L and M non-zero for most of these directions, for all of these directions, geodesics ceases to be global minimizers in the sense that the conjugate points exist. And they ask the question: is it true for the sphere also? And so answer is partially yes, except some low wave numbers, we can find positive curvature in some directions. Any m, which m is smaller than the 1. The same is true for quasi-geostrophic setting. We have kind of conjugate points, positive curvature. And here in this global quasi-geostrophic, we have even more directions for catching. So directions which did not exist in the previous settings. For example, this one, in the direction of this very low number E11. When we perturb it, always we have conjugate. Always we have positive curvature. For the previous ones, yep, if you choose gamma small, then you have. For this low number, yeah, again we see some stability effect, some positive curvature. Let's go to the second central extension and these terms. These terms, they come from a second central extension of the Lie algebra, of quantumorphism group. Oh, no, first central extension of the quantumorphism group and second central extension of the volume-preserving divergence-free vector by some trivial cocycle, capital omega, which is defined using a fixed function phi from S3 to R. If this function is E invariant again, for example, it could be lifted function from S2, and this cocycle can be reduced on S2 also. Specifically, we consider this function for global quasi-geostrophic and this beta times Z, and for the quasi-geostrophic setting, then we end up with using this new bracket. We use cycle omega and also this orthogonal product on the extended space. We end up and using that Riemannian submersion in this new setting. We end up with the quasi-geostrophic equations and global quasi-geostrophic equations as geodesic equations. And again, the solutions exist for all the time and they depend smoothly on the initial condition. The potential vorticity is just this one. You have a bound for uniform bound for this one, then this is time independent. Bound for that one as well. So let's go and see the effect of the rotation. So this encodes this effect of rotation of Earth in quasi-geostrophic equation. And this term in global quasi-geostrophic equation. What we can say about the stability effect of this rotation. So in the sense that we find more directions with positive curvature. So for the usual setting Euler equations, we consider, let's test our method with zonal spherical harmonics. We cannot detect conjugate points, no positive curvature was detected here. But here, yes, when you start rotating the sphere in the right direction and with the right, fast enough, then you can catch conjugate points for half of these zonal flows, those which L1 is odd. For the global quasi-geostrophic, I don't know. I had no time to do the computation, but it seems to me that we have more parameters. The lamp parameter gamma And because Coriolis effect is the same, I think more directions even. And this topography function would be interesting to see that, for example, the role of some mountains, this function h, when you change it, what happens for the motion of this fluid, this perfect fluid on the sphere. So from this point, so I will go to this quasi-geostrophic setting, as I announced. And let's see at least one time-dependent exact solution of this quasi-geostrophic equation, which are called Rossby-Horowitz waves. Here, A, omega, and C are constants, and they should satisfy some specific relation to be solutions of this quasi-geostrophic equations. They are known in meteorology, and usually they use some summation here. Well, if A and C, they satisfy this inequality, then we can catch conjugate points along these exact solutions, time-dependent solutions also. This means that the M criterion works also for time-dependent solutions. This was first written by James Bunn, 2021. Let's give some description for long-time behavior of solutions. So what we can say using this geometry of the configuration space. Let us start with some given solution. For example, this time-dependent solution, Rossby-Horowitz wave, this complex. So using this stream function, we have some velocity field, time-dependent. And we can get a geodesic, eta. Stream function, Eulerian picture, Lagrangian picture. Let's perturb this one, this geodesic, this eta, a little bit. Let's perturb it by some function. Or let's say perturb this function a little bit by, and call it h. This has a velocity field v, and also another geodesic in the diffeomorphism group called delta. So what happens if we have a conjugate point at instant t0? This is the potential vorticity for function f and for function h. It is conserved along the flow with and without this term. In the sense that when you know the geodesic and this potential vorticities at time t0, then you have them at time t also. So if h is a perturbation of f, then the vorticity is the same for f and h at time 0. Since t0 is a conjugate point, then we have this equality, and we have the same potential vorticity at time t0. What does it mean? So this picture. What we see here, it's Greenland, yeah? And here is encodes some Rossby-Horowitz wave at time t0, which is induced by zonal numbers L equal 3 and M equal 2. But this is just the real part of that spherical harmonic at time 0, of that Rossby-Horowitz wave at time 0 with some constants. And these lines, they show the level set of this stream function. This is the level set for z equals 0. So it means that if you perturb this solution a little bit in the directions that the conjugate point exists, and we know that they exist, and after time t0, you see the same picture. It's not something like that you see a different solution, absolutely different solution, like butterfly effect or whatever it is, negative curvature. You see the same picture. And if you catch this conjugate points by that M criterion, then this happens again and again and again. Long time behavior says the same thing. Well, although we could find some positive directions for curvature and some interpretation for solutions, long time, we know that for catching these things, we have to change the parameters to control the parameters in the solution and also in the equation. It's not always possible for atmosphere of Earth, for example. We cannot control those parameters, change the direction of the rotation, for example. So what I see is that in my computations, in most of the directions, the curvature is still negative. Instability. In those directions, like what I have seen in Vienna during the last few days, I think that the curvature was non-negative. -1, 0, and so. Thanks for your attention. And these are some differences that I use. It's taken and published paper. This operator has a special name. It's called Schrödinger zonal Schrödinger operator, subject of English. This was the mathematical derivation of global quasi-geostrophic operations. So the preprint is not yet published. Thanks for your attention.